So the first thing tonight is I picked some homework problems for you, and it's going to look like I picked a lot. No, most of them are multiple choice, okay? So this is homework 5. This is going to be due on Thursday, the 15th. The reason it's not due on Tuesday the 13th is I won't be here. You won't be here. That's fall break, right? Monday and Tuesday the 12th and the 13th is fall break. So after tonight, the next time I see you is on the 15th on Thursday, all right? So I picked one problem out of Chapter 5. Yeah, I know we've been tested on it. There's nothing for you to make, and 533 is on page 154, and they give you the mini-tab printout with the regression line and all that stuff, and then they ask you questions about it. So there's nothing for you to make for that, even though that's out of Chapter 5. And then I went to Chapter 6 here, which are the two-way tables. And I picked all these because these are multiple choice. They give you a two-way table, and they start asking about how many people's in the table, how many people's here, and they calculate some percentages and so on and so forth. So, I just wanted to do that whole string. These are all multiple choice. So, you just do them and give me the answer. There's nothing to be calculated. The two-way table is given to you there. And then the other problem I picked out of Chapter 6 is 6.29. I'd like to have just a word about this problem, because on Tuesday, we'd worked some problems where I showed you like cluster graphs and segmented graphs, and where we were looking at our two categorical variables and we were trying to see if we had any kind of relationship or not. Didn't we do the one about weightlifting, right? The accidental, non-accidental injuries, yep. And then we did the other one that I thought I picked out was something about animal testing, males and females, and how they felt about animal testing, right? So what I'm telling you is I did problem 619 in class, and I did 628, and so I'm picking 629 here. 629 says this: college degrees. Colleges and universities across the country are grappling with the case of the mysteriously vanishing male. So said an article in the Washington Post. Here are the projections of the number of degrees that will be earned in the 2021-22 as projected by the National Center for Education Statistics. The table entries are counts of degrees in thousands. So that's a two-way table, right? The column variable is the gender or the sex, and the row variable is the type of degree. Associates, bachelors, masters, professionals, or doctors, right? Everybody good. Now, you see that little part I read here at the bottom about the table entries are counts. The table is always counts for us when we give you a two-way table of degrees in thousands of degrees. So you see where it says female associates 646? That's actually 646,000. They chopped off the 3 zeros there. Is that going to change what I'm going to do here? No. All right. It says, briefly contrast the counts and distributions of men and women in earning degrees. Are men projected to be vanishing from college and universities across the country? Here's what we need. I'm going to give you some options here. When you do this problem, you're going to need a cluster or segmented bar graph. I don't care which one you give me. Right? That's an or. One or the other. Right? And so what you're going to be showing me is you're going to start comparing conditional distributions here. Well, I'm going to tell you what conditional distributions you need to be comparing, because if you're interested in whether the males are vanishing or not, what you need to look at is you need to compare the 4 conditional distributions of gender given the degree. Now, you notice in this table there are 4 degrees. That's the reason you're looking at 4 conditional distributions. Another way you want to think about this is what you're going to do is you're going to look at the associate's degree. You want to compare the percentage of females that have an associate's degree with the percentage of males, right? You want to do that for each one. So we're looking at 4 conditional distributions of gender or sex given the degree. Now, I'm going to remind you something here. I'm going to show you what you're going to produce for me. Then I'm not going to tell you what the answer is, but what the conclusion is, because it's going to ask you, what's the conclusion here? What do we see here? So if I come over here and I'm in Minitab, if I find this file here, and the file that goes with this is degrees, and this is 629, right? Degrees. That's just like the tables I did that I worked with on Tuesday, all right? So we're going to go to graph, bar chart. You want values from a table, and then you got two choices. We're always doing one columns of values because the counts are in a single column there. The table's not actually put in Minitab like the table in the book. You can do either one. You can do the cluster or you can do the stack. Nobody cares. All right? I'm going to give you this one. And then the graph variable is always the count with these problems. Now, what did I want? I wanted the 4 conditional distributions of gender or sex given the degree, right? So remember, the given part, you put that in first. So we're going to put degree and then their sex. Now, so my head doesn't explode next Friday on the 16th when I'm grading these. Make sure you go to chart options and you show Y as a percent. I want my bar heights to be percents, and then I want the take percent and accumulate across each level. In other words, I want them for each one of those conditional distributions you're going to see, because we're going to see 4 here, right? 1 for each degree. Okay? You click OK. There's a conditional distribution for the associates, for the bachelors, the masters, and professional and doctor. I'm reading it right across the table. And what did we figure inside of each one of those? The percentage of females and the percentage of males, right? That's the heights of the bars there. So what do you think? Are the males vanishing? Do you see how the highest percentage in all the degree levels are the females, and they're mostly over, they're around 60%, and the lowest one is out here at professional or doctorate? And something's going on with the males. You would think if everything was up and up, it would be like 50-50, right? And actually, if we go back 20 years, I bet you the bars flip-flopped. I bet you the higher percentage was males 20 years ago. Here, they're projecting the higher percentage to be females. Are the males vanishing? That's 629, right? And when it says compare counts, give me the distributions. Give me the 4 conditional distributions here, right? Nobody said you had to do all the work and remember, they're there. All I got to do is get my thing to work correctly here. Maybe it won't. Didn't it work on Tuesday? Maybe you'll have to calculate them by hand. Huh. You ain't going to piss me off. I'm sorry, I'm just talking out loud. Just ignore me. Looks like 63% were females there, right? I mean, you can do it out of the table, but it did it for us. Write those conditional distributions down to me, right? 63 there. Look, you know if you've got the percentage of females, then you know the percentage of males, right? Okay? So show those to me. Yeah, they're different. In all the groups, the females are the highest percentage. In this one, they're over 60% females, associate's degree. Here, almost 58%. 62%. Out here, it's a little closer, professional and doctorate, 53 to 47, or 53.5 to 47.5, right? 46.5. So those are your conditional distributions. Show me those. So not only give me the graph, right? This cluster graph or the segmented where they're all stacked on top of each other. Well, there'll be 5 of them that'll be stacked on top of each other there. And then give me the percentage in those conditional distributions. There's 4 of them, all right? Now, we're not done, because hopefully we finished Chapter 8 tonight. Remember, that's the producing data sampling. And so I picked 8.7. We got to do a little bit of work with that one. 8.17, 821. These are both multiple choice. And then 8.24. And hopefully we get through it all so we can do that. Yeah, I know it looks like a lot of problems, but 1, 2, 3, 8 of them are multiple choice. You just read the question, do whatever it tells you, and answer the question, okay? Now, where we left off on Tuesday. So we were talking about sampling. We talked about the population. We talked about the sample. This whole chapter is about how I go from the population down to the sample. The last thing I had written up for you was how to sample badly. And what I meant by that is bad sampling designs. I have 2. We talked about 1. The first one we had talked about was where the guy went to the mall, or I stood outside the library on campus, and that was a convenience sample. That is not good. That's where you're working on getting the easiest to reach, the easiest to contact. There's a second one here, and it's called voluntary response. Sample. Now, the convenience samples, like you're sampling the easiest. Voluntary response, what does that mean to you folks? That means people actually volunteer their response to your question. All right? Like a phone-in poll. Go to this website and vote. Call-in poll, one of those. That's voluntary response. People are picking themselves to be part of the sample. That is not a good thing. Both of these, all right? Both of these. What makes these bad is they introduce, there's a 4-letter word in this class. Bias. We would like to avoid bias. And what bias means is, when we talk about the design of your sample, or the sampling design being biased, what we mean is your sample is set up to systematically favor certain outcomes, to systematically favor one side of the question or the other, right? Well, think about it. You've got a call-in poll. I don't care what it's about, but people are choosing themselves. What kind of people usually call in and vote in some kind of survey or some kind of poll? It means something to them, right? They have a strong opinion about it, and usually their strong opinion about it is they're not happy about it, right? So is that representative of the population? No. Okay? We don't like these two. We don't like this idea of bias. We don't want to systematically favor anything. Because here's the thing. When you systematically favor an outcome in your poll, then you're either going to overestimate what the truth is, or you're going to underestimate it, right? When something's biased, means you're not getting the truth, right? You're not getting the real answer because your sample was pointed one way or the other, yeah? So, depending on which way things are, you could either be way bigger than what the truth is, or way smaller. The fact is, you're biased, right? So you're favoring one side or the other. Okay? That's the point. I just want to get that in your head, that when your sample's biased, when your sampling design's biased, when your sample is biased, when your sample doesn't represent the population, you're going to favor one way or the other, or one part or one outcome, or however many there is. All right? Well, when you favor it, you're either going to overestimate something or you're going to underestimate something. That's what makes it biased. Right? That's what it means to systematically favor some outcome. So if all this is bad, we don't do this. Here's what I'd always tell the students. You read some kind of poll, and you know it's a convenience sample, or you see, oh, hell, these people called in, or they got to this website and voted. You know the results of that poll that are on this piece of paper? You might as well just wad that up and throw it in the garbage can. I can't do anything with that. And what I mean is, You remember on Tuesday I drew the picture of the population up here and the sample down here? And I told you this chapter was about how do you go from the population to the sample. So if you're getting to your sample through a convenience sample or voluntary response sample, in those last 6 chapters of the book where we try to go and infer back from the sample back to the population, you're wasting your time. You didn't have the truth about the population. Hell, your sample didn't even represent it. It wasn't even representative of your population. So I don't care what the work you did in your sample. There's nothing we're going to do to fix this. And when I say fix it, I mean we have no way to fix the fact that your sample is biased here. All right? So, bottom line, as simple as I can make all this, that this is a bad thing. We cannot trust the data from these types of samples. In other words, there's no inferring back. There's no drawing conclusions or saying anything about your population when this happens. It's just no good. Okay? Now, the rest of this is about how do you do this? What's the right way to do this? All right? So we're going to start with the most basic thing I can think of here. Okay? And the most basic thing I can think of is what's called a simple random sample. There's a reason why I circled the word random. Because what we're going to do is we're going to use chance to choose the sample. The other thing we're going to do is we're going to give each individual in the population a non-zero chance of being selected. Now, I'm not saying when I use chance, I'm going to give everybody the same chance. I'm telling you that everybody's got a shot at being chosen. Right? That's what we're saying here. Right? That we're going to give each individual in the population a non-zero chance of being selected. So everybody in the population has a shot at being selected here for your sample. That's what we want to do here. That's the right way to do this. Now, the simplest way to do this, forget simple random sample, forget all that, is take your population, write everybody's name on a little piece of paper, get yourself a big hat, put them all in there, draw names by chance. If I've got everybody's name in a hat, does everybody have a chance of being selected? Yeah, hell, they're all in there, right? Look at it this way. If there's 1 million people in your population and everybody's name is in there, and I choose one out, what's the chance that I choose any one of those million? It's 1 out of 1 million. They all have a non-zero chance of being selected here. Yes? That's the simplest thing we can do. Now, nobody's going to let me keep talking about names out of a hat, so we got to give a formal statistical thought to this, drawing names out of a hat, and that's your simple random sample. Well, on page 208, there is a definition. Now, I don't know if you highlight things when I point things out to you, but you better point this one out, and you better highlight that one, because on your next test, one of the questions on your next test is going to be, well, the definition of a simple random sample is defined to be this. Somebody remind me of that when I get ready to give the test, all right? that I put that definition on there. Okay? Now, it says, I'm not going to write it down. I pointed it out for you. It's the definition of simple random sample. Now, we call it an SRS. SRS stands for simple random sample. This is our basic building block in using chance to choose our sample. This is just like putting the names in a hat and drawing them out. All right? It says a simple random sample, an SRS, of size n. Okay, here's the other thing you got to get used to. Since we're choosing samples now, we always talk about the sample size. And for us, the sample size is always denoted by lowercase n. That's how many individuals in your sample. That's how many you're dealing with in your sample. It says a simple random sample of size n consists of n individuals from the population. Of course it does. It has n individuals in it, right? Chosen in such a way that every set of n individuals has an equal chance to be the sample actually selected. Now, note, it doesn't tell you about the chance of any one individual in the population being selected. Let's do it like this. Can I put some numbers to this? Let's say you got 1 million people, and you're going to choose 100 of them, right? So you start choosing 100 names out of the hat. You choose another number. You understand that this sample here has the same chance of being selected as this 100 does, yes? A simple random sample would give any sample chosen this way, any sample of size 100, the same chance. Let me ask you this. Let's just deal with something local here. Let's say we're in Washington County, and I want to choose registered voters, and I want to choose 100 of them, and I'm going to choose a simple random sample of 100 of them, right, out of Washington County, okay? Is it possible that all 100 of them come from Johnson City? You know, Johnson City's in Washington County, right? Yeah? Is it possible all 100 of them come from Johnson City? Yeah. That 100's got the same chance as any other 100 as long as I'm doing a simple random sample, right? They could all 100 be from Johnson City. They could all be scattered all through the county. They all have the same chance. That's what makes a simple random sample a simple random sample. It gives every set of whatever sample size you're looking at the exact same chance of being selected. Okay? Now, there's a note that goes along with this little definition here, right? And the note is an SRS gives every individual an equal chance. That's not the definition, but that's a little fact that goes along with the simple random sample. Not only does a simple random sample give every set of whatever you're looking at the same chance, but it gives every individual in the population the exact same chance. Okay? Now, I have a reason for mentioning this. It's going to take me a couple minutes to get there, but I have a reason for mentioning that little fact, that little note about a simple random sample. Think about it like this. A simple random sample doesn't leave out any part of the population. Right? Everybody in the population's in that hat. We didn't leave out anything. Okay? Now, does everybody got their book open on page 208? They're going to talk to you about random digits. And they're going to talk to you about a table of random digits. Okay, here's the first thing. A digit is a number from 0 through 9. There are 10 digits, right? When they think about a random digit, it's like you've put 10 numbers in the hat, 0 through 9, and you've drawn them out. What's the chance of any one of those digits being drawn out when there's the numbers 0 through 9 in your little hat? The chance of any one of them getting chosen is 1 out of 10, right? Every number's in there one time, and there are 10 numbers. I'm trying real hard not to say the word probability and just say the word chance. If I let the word probability slip out, you slip in chance, right? So the chance of any one of those 10 numbers being drawn is 1 out of 10, yeah? So what they do is they make a table of random digits. We need this to choose a simple random sample by hand. All right? Now, in the back of your book, there's a table B in the back. And I'm assuming table B is right after table A. There's also a table B in your little formula sheets, but for what we're doing in the book, we'll look at the one in the back of the book. I think that has more lines. And if I come back here and I find this table B, it's on page 700, I'm assuming. It's a table of random digits. Now, the first column is line numbers. You know, they go from 101 down to 150. Now, why in the hell would this table have line numbers? It's so all the problems tell you where to start. See, if I start on line 105 and you start on line 107, we're going to get different answers here. Remember, it's a table of random digits. If you want to think about how this was made, somebody stood here with the hat, and the digits 0 through 9 in here, they drew one out. Oh, the first one was a 1. They put it back. They shook the hat. Oh, the second one was a 9, right? They drew them out one at a time. You know, some computer generated this, right? But that's what it was doing. It was generating random numbers between 0 and 9, right? Those whole numbers. Does everybody see how they're grouped in groups of 5? Let's pick a row here. You see like 105? You know, it's 95592. Is there anything special about them grouping in 5s? It's to help you read it easier. So they're not all just strung together. They put them in little groups of 5 so that you can read them, right? Now, when I look at 105, at any spot that I would pick, the chance that any one of those 10 digits would show up there is 1 out of 10. How do I know that? There's 10 digits, and each one of them is only listed once in my hat, right? Now, I can read the table as single digits. Like I can read 105 as a 9, a 5, a 5, a 9, a 2, a 9, a 4, a 0, a 0, a 7. I can also read the table as pairs. In other words, I can put two digits together, and I can read this as 105. I could read as 95, 59, 29, 40, 07, 69, 97. Everybody understand? Depending on what I need to do, I can read them as singles. I can read them as pairs. What's the chance of any one of those pairs showing up anywhere in this table? How many pairs are there? There's 100 of them. Think about it. I got 100 little sheets in the hat, right? I got the pairs on there. It's 1 out of 100. I can read the table as triples. I can read them 3 at a time. So I could take 105 and I can read that as 955, 929, 400, 769, 971. What's the chance of any one of those triples showing up anywhere in the table? How many triples are there? There's 1,000 of them, right? The chance of any one of those triples showing up anywhere in this table is 1 out of 1,000. Can I read them 4 at a time? I can read them however I want. Hell, it's a table of random digits. They just put them in rows so that we can all get the same answer. Could I read down the columns? Well, hell yes. It's a table of random digits, right? There's nothing special. But we read across the rows. Now, that's our table of random digits. It's just like a pile of numbers, right? The digits 0 through 9. They got a chance of 1 out of 10. If I read them as pairs, they got a chance of 1 out of 100. If I read them as triples, they got 1 out of 1,000. If I read 4 at a time, that's 1 out of 10,000, right? Of any one of those showing up. Now, we're going to need that guy because when we go to choose a simple random sample by hand, right? Choosing an SRS, a simple random sample. This idea of drawing names out of a hat. All right? So, there's 2 things that need to happen. 1, we need labels for the individuals in the population. And when I say labels, I need numbers. I need to assign a number to every individual in the population. The catch is, each label has the same number of digits. Right? So if I have 100 individuals in my population, how am I going to label them? You know I have to go from 1 to 100, right? 100 is the biggest one, and to write the number 100, I need 3 digits, right? So I'm going to start out labeling as 001, 002, because every label needs to have the same number of digits. If I've got 1,000 individuals in my population, I want a number from 1 through 1,000. But 1,000, I need 4 digits. So how am I going to write these other numbers? It would be 0001. Everybody has to have the same number of digits in their label, right? So we're assigning them a label, a number. And 2, use table B. Now, I know they do example 8.4, sampling spring break resorts. I would rather do this. Let's come over here to page 210. All right? I want to give you a second one here. If I look at page 210, and I want to look at problem 8.6. Because you're going to do 8.7 for me for homework. Here's what it says. Apartment living. You are planning a report on apartment living in a college town. You decide to select 3 apartment complexes at random for in-depth interviews with residents. Use the simple random sample applet or software or table B. Sorry, we're table B here. We're going to do it by hand. To select a simple random sample of 4 of the following apartment complexes. Did anybody see a problem with what I just read? You would have thought this dude would have corrected this by now. I'll read it to you again. You are planning a report on apartment living in a college town. You decide to select 3 apartment complexes at random for in-depth interview with residents. Use a simple random sample applet, other software, or table B to select a simple random sample of... Dude, I would have thought the author would have caught this one. That's been in this book for like editions. So what we're going to do is we're going to do 4, okay? Because it says select a simple random sample of 4. So what we need is we need an SRS, simple random sample of size n equals 4. So what they have for us here is the following apartment complexes. There is your population. They've listed your population for you, right? So there must be Ashley Oaks, Bay Point. How many are in this list? 2, 4, 6, 8, 10. There are 30 individuals in your population, and we're trying to choose a simple random sample of 4 of them. 30 in the population. So I'm going to go back to how do I go about choosing a simple random sample? I mean, I know I want one of size 4 here. We have to give every individual in your population a label. You understand, if there's 30, I want a number from 1 through 30, correct? So here's the way I would do it. I would start at this first column and I would number 1 through 10. The catch is everybody's got to have the same number of digits in their label. So I would go 01, 02, right, all the way down to 10. I would come to the second column and I would label them 11, 12, 13, 14. I go to the third column, 21, 22. Does everybody understand what my little dots is? That means I was too lazy to write the rest of them, but I labeled them all. I went from 01 to 10, 11 to 20, and 21 through 30. Does everybody have a label now? Does everybody have a number attached to them in the population? Yes. Does everybody have a number that has the same number of digits? Everybody's got 2 digits, right? The reason they have to have the same number of digits, when I go to table B, I'm going to read them as pairs. Why am I going to read them as pairs? My labels are pairs. I don't use any more digits than are needed. That's the reason I keep asking you, how many's in the population? There was 30. I need the number 30. I'm going to have 2 digits. If there was 130, I would have 3. If there was 1,000 and whatever, I'd have 4, right? And I always start with 1 and go to there, and then I put the zeros out front so that everybody has the same number of digits. You notice I got 01, 02, 03. That's the reason I did it like that. Now, If they don't tell me what line number to pick here, where to start in your table, I'll never be able to check your answer. You notice it says start at line 128. So we're going to work with line 128 in table A in the back of your book. Line 128. If we all start on the same line, we all get the same answer. We can check the answer then. Now, I know when we go back here and we look at this table, right? When I look at line 128, there's just a whole pile of numbers in there and they're grouped by fives to make things easy to read, correct? So what I'm going to do is I'm going to start on line 128, and when I look at line 128, I'm going to read things in terms of pairs. So the first pair I see is 15, correct? The next pair is 68, 91, 42, 27, 06, 56, 51, 43, 37, 41, 33, 52, 49, 36, 78, 19. Yeah, I'm going all the way to the end of the row here. 82, 87, 20. Oh, I screwed that up. 82, 87. I screwed that up. Where did I screw it up? That's not good. 15. Somebody read these to me. 15, 68, 91, 42.
There's 43 to 74. Second.
Here? Down here? I'm going to get them right. 15, 68, 91, 42, 27, 06, 56, 51,
Second row, second column.
43, 74. Here?
Yeah, actually 72.
And then what's the next one? 13? These will all be wrong. Sorry. 74, 13, 35, 24, 93, 67, 81, 98, 28, 72, 09. I went across and read them as pairs. Okay? Now, here's what you do. You start at the beginning, and you ask yourself, I got 15 as one of the numbers out of my random digit table. Do I have anybody that has a label of 15 in my population? Remember, they went from 0, 1 to 30. So you're going to pick the individual that has a label of 15. All right? Do we have anybody that has 69, 68, 91, 42? All those are no, right? You have somebody that has a 27, correct? You're 0, 1 through 30 on your labels. You got 0, 6. There's no 56, 51, 43, 74. There's somebody that has a label of 13. Are we done? How many are we choosing? You're choosing 4, right? So we're going to pick the ones that have 15, 27, 06, 13. So you go back to where you looked and said, okay, I labeled these 0, 1 to 10, 11 through 20, 21 through 30. Who's got a label of 15 back here? It shouldn't be too hard to count down and figure it out. 11, 12, 13, 14, 15. It looks like that is, what is that, Farrington? That's your 15. Your 27 is Sagamore Ridge. The one that has a label of 06, Briarwood. And the one that has a label of 13, Crestview. That's your simple random sample of size 4. Yeah, bud.
What happens if you get two of the same number?
So I got two things that come up. I got the question here is what happens when you're reading across here, right? And you started out and you pick 15. Maybe 15 shows up in your list again before you get to your 4. You can't pick that one again, right? So you just mark it off. You already got that one, and then you just keep going. So if it repeats before you get to the 4, however many you're choosing, I know that gets a red line because you can't pick him twice. The other thing is this. What would happen if I got to the end of this row, this line 128, and I didn't get my 4? Where do I go? Go to line 129 and start reading his pairs. Go to the next line. Yeah? So 2 things is, if it repeats, you only get to pick it once. After the first time, just mark it off. If you happen to get to the end of the line that they tell you to use, then you don't have the 4 or 5 or 10 or whatever you need, start on the next line and read them as pairs. Does everybody understand why I read things as pairs? It all comes back to what was my labels. They were pairs. If my labels had been triples, I'd have read them as 3 at a time. Then I'd have went across that whole row. I'd have come back and asked myself, do I have anybody that has that label? Yes. I circle them. The ones that don't, I just mark them off. That's how you do it. Now, I'm going to give you an obvious fact here. The larger your population is, the harder this little handwork becomes. Well, think about it. Can you imagine you got like 1,000 people in your population? You got 0,001 up to 1,000? No, it's usually small, like 30. The one you're going to do for homework has 2, 4, 6, 7, 14, like got 26 in it or something like that, right? You're going to do 8.7. I assigned that for homework. It's the same thing I just did here. 8.7 is minority managers. A firm wants to understand the attitudes of its minority managers towards its system for assessing management performance. Following is a list of all the firm's managers who are members of minority groups. Use a simple random sample Atlas, other software. You're going to use table B, and you're going to start at line 141 to choose 5 managers to be interviewed in detail about the performance of the appraisal system. What's your sample size here? N is 5. How many are in here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There's 26 individuals in your population for that problem. You're trying to choose an SRS of 5 of them. How are you going to label these? Please label 01 through 07, 08 through 14, 15 through 22, I think it is, and then 15 through 20, and then 21 through 26. That way I'll know what you did when I start looking at your answers. So just like I went down the columns, would you please go down the columns, right? So that make my life a little easier. You're going to go to table B, and you're going to go to line 141, and you're going to read them as pairs. Exact same problem as we did here. And then when you're done, tell me who we're looking at. Just don't give me the numbers, right? Tell me, okay, this label was attached to this particular manager. Yeah.
Do you want us to write all these down with the numbers?
Oh, no. I'm good. No, so she's asked me about the problem. Do I want to see that? No. I'm telling you that you got to at least tell me you labeled things 01 through 26, right? And then you can tell, you can write it, and then you can write it on there, and then go through, and then tell me what you did, and then give me the 5, and then give me their names. Now, No. Yeah. That takes care of the simple random sample. All right? Here's what I want to do for a second. Look, the simple random sample is not the only one. There's other sampling designs. The simple random sample is your first good sampling design. It used chance. It gave every individual a population of being chosen, right? So that's a good thing. You see example 8.5 on page 210. In general, do you think gun control laws should be made more strict, less strict, or kept as they are now? When the New York Times and CBS News asked this question of 1,644 adults in February 2014, 54% said more, 9% said less, and 36% said keep as they are now. Can we trust the opinions of this poll to fairly represent the opinions of all adults? Okay, here's part of the statement by the Times on how the poll was conducted. See, what they're getting ready to tell you now is, how'd they get that 1,644 adults they asked that question to? The latest New York Times CBS poll was based on telephone interviews conducted February 19th through February 23rd with 1,644 adults throughout the United States. Okay? The sample landline telephone exchanges call was randomly selected by a computer from a complete list of more than 81,000 active residential exchanges across the country. The exchanges were chosen as to ensure that each region of the country was represented in its proper proportion. Okay, so they called phone numbers, and they did that they generated random phone numbers. All right. Within each exchange, random digits were added to form a complete telephone number, thus permitting access to listed and unlisted numbers alike. Within each household, one adult was designated by a random procedure to be the respondent. So look, the word I'm looking for when I read shit like this is the word random. Well, they got it in here like 2 times already. All right? It says cell phone numbers were generated by a similar random process. The 2 samples were then combined and adjusted to ensure proper ration of line lines and so on and so forth. I have a question for you. When they're doing this and they're calling phones, and I know they're generating random numbers, I know they're generating random cell phone numbers, are we leaving anybody out? People that aren't home, right? People that don't have a cell phone and don't have a landline. You know there's still people in this country like that, right? That don't have a phone of any kind, right? You do understand that there's a little bit of bias here, right? Because there was a group of people that we left out. People didn't have any type of phone. But we're willing to live with that the way things are these days, right? So this idea of random digit dialing, that's about as good as we can get when we're going to talk to people either on their landline or when we're going to talk to them on their cell phone. Yes, you've got to keep it in your head. There's a little bit of bias here because you left out somebody didn't have any type of phone, right? You understand why that would be biased? Because if you get those people in there, right, the people that never had a chance, could they change the poll? Yeah. Could they confirm the poll? Yeah, you don't know which one, right? So that's a problem. Random digit dialing is about as good as it comes, okay? Now, before we do any other sampling designs, always ask, how was the sample chosen? Now look, nobody's going to tell you they used a simple random sample or any other good sampling design. But what you're looking for is, you want to see, why do you want to see random? That means they gave individuals in the population a chance of being selected. Yes, I understand with random digit dialing they had a little problem. But in the big scheme of things, not that big a problem. When I see the word random, I trust the results. Look, I don't want to see convenience sampling. I don't want to see voluntary response. I don't want to see people calling in. I want to see somehow they randomly chose phone numbers and called them, right? I want to see the word random. It just makes me feel better about things. They use some kind of chance, all right? Now, you see this on page 211? It says inference about the population. Now, we're a long way from doing this. About the population. There's a couple things I want to have stuck in your head at this point about this idea. And one thing is this, is what we're talking about with inference. What that means to us. It's statistical inference. What that means is using information from a sample. Remember the smaller group that we work with, to draw conclusions about a population. That's what inference means. That's what we're trying to do here. Okay? Now, what the parts I want you to think about now is, one, we would like trustworthy results. That's what we would like, right? If you're going to do this, if you're going to take the information that you learned about a sample and try to draw conclusions about the population your sample came from, you'd like to trust that, right? So at this point, what I'm telling you is, not in those words that we would like trustworthy results, we would like the sample to represent the population. That's what we would like. I mean, that's our first step to trusting things, is that the sample you chosen was done in a random way, used chance. And so our sample, we want it to represent the population. We want to be unbiased, right? We don't want any kind of bias in this whole deal. Now, the next two, this is not the only time you're going to hear me say the next two. Never exactly correct. So when you take what you've learned about a sample, and I don't care if the sample represents the population as good as it can, you're never going to be exactly correct when you go back from your sample to your population. You're never going to be exactly, never. Okay? 3. If we did it again, if you took a different sample, we get a different result. For example, let's say we were looking in the state of Tennessee, and we want to get a feel on what the people in Tennessee think about the governor's job. So like the governor's approval rating. So we decided to choose a random sample from registered voters in the state of Tennessee. Let's say we choose 1,000 of them, right? We can do a simple random sample. We choose 1,000 of them. And so we ask them that question. Yes, he's doing fine, or no, he's not doing fine, right? And so we get like 63% of the sample that says the governor's doing fine. Now, number 2 says, when I take that 63% approval rating of the governor and I try to go back to all registered voters, is it exactly 63%? That's what I mean by you're never exactly right. Suppose I take a different sample of 1,000 registered voters and ask them the same question. Do you expect them to be 63%? This one might be 61. It might be 67. It might be 52. Every time I take a different sample, I get a different approval rating, right? Okay. Now, usually I point out to students that those two, this whole idea of me wanting to take what I learned from the sample and say something about the population, dude, you're nuts. You're never exactly correct, and if you take a different sample, then you get a different answer, a different result. Really? And you want to do this? Yeah, I want to do it. The reason is, and I'm going to put this exactly in my language, probability Remember, the title of the class is Probability and Statistics, right? You ain't seen no probability yet. That starts in Chapter 10. Before we start doing inference, we learn about probability because probability plays a role here on the issues we have with 2 and 3. 4. We always give a margin of error with our results. What I mean is when we start telling people about this inference from your sample back to your population, we don't give you just one number, we give you a range of numbers, and then we attach a probability to that. Right? So that's the reason why we need to stop off and talk a little bit about probability. Okay? And then the fifth one is the one out of all these I'm listing here, it's the most important one at this moment. Larger samples. And I'm going to put random just so that you know that when I'm talking about something good here, it's a random sample. Larger random samples give more accurate results. Now, here's what I mean by this. Think about it for a second. Here's your population. You got a sample of 100, right? And you figure out the approval rating and you try to go back. You understand, if I took a sample of 1,000, that would be more accurate, right? If I took a sample of 10,000, why is that? Because the more individuals from the population that I can get into my sample, the more accurate my results are. I can't show you a formula at this point. You just got to take it on my word is. Look, the more individuals I can get from my population in the sample, when I go to infer back, the better my results are going to be because I have a better picture of the population with more individuals in my sample, right? That's what the deal is here. The more individuals I can get in my sample from my population, the better my answers are going to be. The more accurate they will be. Eventually, I'll come back and show you a formula that says, you see this right here? You remember in Chapter 8 when we was talking about larger random samples give more accurate results? Here's the formula that says that. This is what this formula is showing you here, right? That your answers are more accurate the larger your sample size is. Okay? Now, like I said, this is the part you want to think about here in this chapter. The one about the margin of error, hell, we talk a whole thing about that. That's like chapter 13, 14. This idea of 2 and 3, never exactly correct, different sample, we get a different result. We get to talk about that a bunch of times too. Hell, number 1's got to stand with us from now on, right? We want to trust our results from our sample to infer back. So the big one is larger samples will produce more accurate results. Now, while I'm jabbering about that, okay, and when I say jabbering, I mean down here at the bottom, larger random samples give more accurate results. Does anybody know what a census is? While we're here, you ever heard of the current population survey census that they do? What are we trying to do when we do a census? Let me ask you this. When the government does a census, are they taking a sample of the households or anything like that? No. When somebody's doing a census, there's no sample involved. There's no inference. Because with a census, try to collect info on each individual in the population. Nobody cares about time and money at this point. We want to talk to every individual in the population when somebody is doing a census. There is no sample. There is no going from your population down here and answering the question and trying to infer back. When you're dealing with a census, you're working with every individual in the population and you're trying to gather information on every individual. There's no inferring back from the sample. It's the census. You talk to everybody. You work with everybody in your population, right? Now, when I have these other sampling designs, okay, the simple random sample was number 1. So I'm going to do this. Good sampling designs. The first one is your simple random sample. The second one we're going to talk about is called the stratified random sample. Still that word in it. Stratified random sample must use chance, right? That's what makes it a good sampling design. Now, in a stratified, look, the simple random sample, you can think about it as throwing all the names in the hat and drawing out as many as you need. That's what you do when you're using the labels in Table B. All the numbers are in a hat and you're pulling them out, right? The names are in the hat and you're pulling them out. Stratified. Here's the difference. Okay? The first thing we do is we divide the population into similar groups. They have a name called strata. So as soon as you see somebody trying to choose a sample, and the first move they make is they go to the population and they start dividing them up into similar groups, like they divide the men and the women, or maybe they divide by age group. At the university, maybe we divide by your year, or freshmen, sophomore, juniors, and seniors. As soon as you see them starting to divide the population up into these groups, you need to start thinking this is a stratified random sample, because then what you do is you choose a sample, a random sample, and I'll be honest with you. With what we have, you choose an SRS from each strata, and then combine to form the full sample that you are looking at. So you've got these groups, 2, 3, 4 groups. You're going to take an SRS out of this group, one out of this group, one out of this group, and when you're done, you'll put all those 3 together, and that will be your stratified random sample. That's how it works. So, I know the book's got one here about seatbelt use and all this. Here's what I want to do. All right? Let's say we're at ETSU, and I want to get undergraduates' opinions about tuition cost. Okay? Now, I could just choose a simple random sample of undergraduates, correct? Maybe 500 of them. Let's say 400. But when I do a simple random sample and I give every undergraduate a label, is it possible that all 400 of them are freshmen? Yeah. Is it possible all 400 of them were juniors? See, the simple random samples are building block. We want to do better than that, right? We want to make sure that we have freshmen, sophomores, juniors, and seniors, right? So we want to do a stratified. Yeah. So here's what we're going to do. I'm going to do it like this. Here's set your population. This is ETSU undergraduates. And so that I can be sure that I go across all 4. And what I mean all 4 is freshmen, sophomore, juniors, and seniors. Is the way to do this is stratified. I don't want one level to be more prominent than any other, right? I want to be the same. So we're going to take this and we're going to divide them up into these strata. Freshman, sophomore, junior, senior. Okay? So we take all the freshmen. We give them labels. I don't know how many freshmen we got. We give them whatever labels we need. What we're going to do is we're going to choose an SRS of size n equals 100. Just on the freshmen, right? I got my population. I got this list of the freshmen. And I'm going to give them all labels, and I'm going to choose a simple random sample of 100 of them. Just like I did with, apartment complexes back there, except now I got maybe 4,000 of them, right? I want to do the same thing with the sophomores, right? I got all the sophomores. I got their names listed. I'm going to give them all a label, and I'm going to choose an SRS of size n equals 100, right? So now I'm doing this separately. It's like I'm starting all over, right? I'm assigning labels. I'm picking a different line number in table B, right? I'm going to do the same thing with the juniors. An SRS of size n equals 100. And then we'll do the same thing with the seniors. SRS of size n equals 100. Right? So we did each strata by themselves. right? Simple random sample within each group. Then you take these. There's your sample. Of 400 students. Now, what am I guaranteed of by doing this? I would have 100 freshmen, 100 sophomores, 100 juniors, and 100 seniors. What's my total sample size here? 400. So I'm guaranteeing to have 100 in each one of the groups. Does that make sense? It's like going to the state of Tennessee and going back to the governor's approval rating. And let's say I was going to choose a sample of 1,500 registered voters. If I do a simple random sample, right, just the basic names out of a hat, everybody's got to understand it's possible all 1,500 of them come from Nashville. Yeah, hell, that sample size 1,500 has the same chance as any other 1,500, right? That's what makes it a simple random sample. What's a better way to do it? Well, we would like to have registered voters from all over the state, right? Is the state already normally broken up into counties? Couldn't I take my strata to be the counties and take so many each county and then put them together to get my sample? Is that a better picture? Is that a more representative sample? Look, they both use chance. The problem with the simple random sample, it's so simple that sometimes you can actually get a bad sample. Like all 1,500 of them, hell, they're from Nashville. Or all 1,500 of them are from the western part of the state. That's not good. Stratified random sample actually improves on the simple random sample. You make groups. Okay, I got my groups here. I'll take the counties, and I'll choose 20 out of each county, and then I'll combine them, and that's my final sample. Now I know I got registered voters out of every county in the state. I gave you, freshmen, sophomores, juniors, and seniors. Would it make sense sometimes to divide the population up into men and women? Choose so many men, choose so many women, so that then I have both genders involved? Yeah. Right? So it's an improvement. They both use chance. The simple random sample is an improvement. Now, here's what I want to do. I got 2 more sampling designs, but I'm not done screaming about this stratified yet, because you'll notice inside of here, I've used a simple random sample within each one of the groups, each one of the strata, to choose my sample out of those, and then I combine them, right? So my question is how do I know that this stratified random sample is not a simple random sample? So what we're going to do is we're going to come to your homework problems. Look, what other problem did I assign for homework? 817 or something? That's multiple choice, so you're okay. It's 821, I think it was. I want to come over here, and I'm looking at, I'm on page 223. Okay? And there's one I want to look at here because I want to scream at you a little bit about this. I don't know if it'll do any good, but I'm going to. I want to look at 8.37. Okay? It says, at a large block party, there are 40 men and 30 women, right? I got 40 men, 40 males, 30 females. Yes? That's what it's telling me. That's my population. You want to ask opinions about how to improve the next party. You choose at random 4 of the men and separately choose at random 3 of the women to interview. You want to choose 4 men and separately 3 women. Okay? It says, what is the probability that any of the 40 men is in your random sample of the 4 men to be interviewed? How many men were there? 40. How many are you choosing? 4. So what's the chance of any one of those men being chosen? In my little world, it is every man has a 1 in 10 shot. Agree? Because you're choosing 4 men. Hell, there's 40 men in the party. 4 divided by 40 is 1 out of 10. It says, what is the probability that any of the 30 women is in your random sample of 3 women to be interviewed? How many women are you choosing? 3. How many are total? So if you're a man, you have a 1 in 10 shot. If you're a woman, you have a 1 in 10 shot. So anybody at the party has a 1 in 10 chance of being selected. Everybody agree? Yeah. Okay? Now, if you've done the calculations correct in Part A, and I sure hope we did, the probability of any person at the party being interviewed is the same. They all have chance 1 out of 10. Yeah? But the punchline is, why is your sample of 7 men and women not an SRS of the people from the party? Well, the answer to this question is not that it's a stratified random sample. We know it is. We know it's a stratified random sample, right? This is, when you did this, and here was the party, here was your 40 men, here was your 30 females, you chose 4, you chose I'm just going to say people. I was going to say drinkers, but it might not be that kind of party. Okay? So you chose 7. Now, I didn't write SRS. All I know is they did it in a random thing, right? So we went down, took 4 of the men, we took 3 of the females. So you can see that, hell, that's just the same picture he drew with freshmen, sophomore, juniors, and seniors, right? It's a stratified random sample. But that's not the answer. When it asks you why it's not a simple random sample, you cannot tell me that, oh, well, hell, it's a stratified random sample. That's not the answer here. Now, does everybody remember the definition of a simple random sample back on page 208? See, you've got a sample of 7 people here, right? That's what you're trying to do. You got 70 people at the party, and you're trying to choose 7. So in a simple random sample, every sample of size 7 has the same chance. Yes? I don't care what the chance is, but every sample of size 7 has the exact same chance. Is that true with the stratified? Is every sample of size 7 have the same chance with a stratified random sample? And the answer is no. The problem with stratified is, what we just did here in this picture, there are samples of size 7 that have a 0 chance of being selected. That's always the punchline when somebody says, okay, you're looking at this new sampling design. Here's stratified. Yeah, you could all see it, right? They did the men, they did the women, and they got 7. The answer is always, whatever sample size you're looking at total, and the total you're looking at here is 7, because you're going to have 4 men and 3 women. The problem with the sampling design you're looking at, the reason it's not a simple random sample, is because there's samples of that size that have a 0 chance with whatever method you're using other than a simple random sample. You understand what happens every time I do this? Every time I do this with a stratified random sample, I get 4 men and 3 women, yes? You do it again, hell, I get 4 men and I get 3 women. Do it a third time, I get 4 men and I get 3 women. If I was doing a simple random sample and I had all 70 people labeled from 0, 1 through 70, is it possible to get 5 men and 2 women? Is that happening with the stratified random sample? If it's not 4 and 3, it's not happening. Is it possible to get 2 men and 5 women? Yeah, with the simple random sample it is. That's the reason for me saying, look, with the stratified random sample, there are samples of size 7 that have a 0 chance of being selected with this stratified random sample that we're looking at here. That's what makes the stratified random sample different from the simple random sample is. It doesn't match the definition. With a simple random sample, whatever size you're looking at, they all have the same chance. Right? Stratified, some of them have the same chance, and some of them are never going to happen. Right? Simple random sample, I can have 5 and 2. I can have 3 and 4. I can have 1 and 6. Right? Stratified, it's always going to be 4 and 3 in this example. So you got samples of size 7 here that's got a chance of 0 of ever happening. That's what makes them different from each other. Okay? Now, that's the second good one, stratified. The third one is something called a systematic random sample. Yeah, we like to throw that word random in our good sampling designs. At least 3 out of the 4 we're going to look at has that. All right. Now, the only place this systematic random sample shows up, it doesn't show up in the middle of this chapter, right? It's not even in there. The only place this is it's on page, it's in the homework problem. It's on page 224. And it starts out in example exercise 8.43. That's the only place this shows up. Now, here's the way I'm going to do this. All right? You can look at this 8.43. That's a systematic random sample. It's different than a simple random sample. It's different than a stratified. Here's the way I think about this, right? Where when I think about when somebody says, well, you're looking at a systematic random sample, here's what I'm thinking. Is I have my population all numbered and they're all in a row, right? So I got like this long list of the population. And what I do is I pick a number, a random number, let's say between 2 and 20. You know, out of a hat, put the numbers 2 through 20 in there, pick one out. Maybe I pick an 8. And so what I'm going to do is I'm going to pick every 8th person. So I'll pick the 8th one, the 16th one, the 24th one, the 32nd one. That's systematic random sample. So you've got them in a list, and then somebody tells you which number to pick. It's like this. Let's say we work at the Twinkie factory. Do we still make Twinkie? They still make Twinkie? Let's say we work at the Twinkie factory, right? Now you know they must do some kind of quality control, yes? To make sure the Twinkies are yellow and firm and soft and have the right amount of cream in them, there must be some kind of quality control there, yes? Now, you understand that when you're working at the Twinkie factory and you need to check quality control, you can't do a census. You understand why you can't do a census? Then you got no Twinkies to sell. You done checked them all, tore them apart, and measured them all, right? So what happens is they don't do like put them all in a big pile and do a simple random sample. What they do is there's a guy standing at the end of the thing. And like today, okay, today's Thursday. Oh, we're going to pick every 10th one down the row, right? So the 10th one comes, we pick it up. The 20th one, we pick it up. 30th one, until we get our sample, however many we need, right? That's a systematic random sample. When you read the one in the book, it don't read that good, but that's exactly what they're doing. We're picking so many down the list, or so many down the list of our population. We did a random number depending on how many we need. You know, we might pick every 5th one, every 8th one, 12th, whatever it is. You're picking down the list, and that will form your sample. You understand why that's not a simple random sample? Because if you're picking every 5th one, you're not going to get the 5th one and the 7th one, are you? You're going to get the 5th, the 10th, whatever. There's samples of whatever size you're looking at here that have, it's the same story as this. What makes a stratified not an SRS? What makes a systematic? There are samples of whatever size you're looking at that have a 0 chance of happening. Simple random sample, they all have a chance. They all have the same chance. Okay? Now, I'm going to stop there. There's a 4th one. It's called a multi-stage sample. They actually leave the word random out. Okay? We'll pick up there next Thursday, the 15th. Don't forget my problems. I think we're okay that we got far enough in Chapter 8 that you could answer all them. And the only one you might have a little questions about is 824. Right? That's a multiple choice question. That's the last one I'd given you, right, for Thursday. And we've actually talked about it. It says a sample of households in the community is selected at random from the telephone directory. In this community, 4% of households have no phone, 10% have only cell phones, another 25% have unlisted. The sample will certainly suffer from, what's the problem here? I mean, I haven't mentioned these terms yet. Non-response just means people aren't going to answer. Undercoverage means you left out a group of people. And false response, I don't know what the hell that is. Okay? So anytime you're going by the phone and you got unlisted numbers and you got a bunch of people who don't have any phones, you got a bunch of people that have cell phones, right? And you're going by the telephone directory, you got a problem, and it's because you've left out parts of the population. You're suffering from undercoverage. Okay? Everybody have a good weekend. We'll see you on Thursday. Be careful going to the house. She's kicking stuff.
That's been my day all day today.
Dropping?
Yeah, it's taking a whole lot anyway.
Yeah, Mike.
Yeah, bud, what?
Were you hollering at me?
No, man.
Okay.
I was talking to myself. Sorry.